Thank you.
Okay, so tell me if I'm wrong, but in this class we've talked about row space, column space, and all that. So given a matrix, what is the row space or column space of the matrix? And let's use the letters C, S, N, S, and R, S. Column space of the matrix A is the span of the columns of the matrix. I'll write in a sentence. Span of the columns So row space of the matrix then must be the span of the rows of it. So here we're looking at the matrix and we're either thinking about it as consisting of column vectors, and the span of those columns is the column space of the matrix. Or in this case, we're thinking of the matrix as consisting of row vectors, and the row space would be the span of those rows. And we already defined null space. So the null space was the all solutions to the equation AX equals 0. And now, what is rank? So not how to compute rank, I guess, for now, but just the definition of rank. Rank is the dimension. So the rank of a matrix is the dimension of the column space of the matrix. Right? Because, I mean, the span of the columns creates a subspace. And so that's a vector space in its own right, and we want to talk about the dimension of that subspace, and that's called rank. As it turns out, the dimension of the column space and row space are the same. They're not the same spaces, but they have the same dimension. And the nullity of a matrix is the dimension of the null space. Again, null space being a subspace, so we can talk about its dimension. So those are the definitions. So suppose we have a set of vectors. Okay. So also because we're talking about subspaces, we're going to find bases for these. The basis for the row space, the basis for the column space, the basis for the null space. So let's start with a matrix A. This is a 4 by 5 matrix. And so we want to talk about the row space and the column space of this matrix. So the column space is going to be a subspace of what vector space? So the column space, conceptually, will be a subspace of what vector space? R to what? What dimensional open space? Four. Right. I mean, columns are in R4, right? So their span is going to be a subspace of R4. And the row space of the matrix will be a subspace of how many? Yeah, the rows are vectors in R5, right? So the span of them will be a subset of R5. So right away, you can kind of see why the column space and the row space, even though they have the same dimension, are not the same thing, that they're not even the same parent space. So, so how can we find the basis? This is really the fundamental kind of operation or the computation you're going to be doing in these sections in this homework. So how do you find the basis for the column space and row space? Yeah, you reduce the matrix. So you would row reduce, and you get some result, which is like this. And using this matrix and the original one, we can find a basis for both column space and row space. Okay, so here's the key: a basis for the row space consists of the non-zero rows of the reduced row echelon form, or just row echelon form, either one, where spaces aren't unique, right? Okay. So the basis for the row space in this example would be set, right, where the non-zero rows are bases. I'll write them as columns because these are vectors in R5, so your book does it that way. I'll do it as well. This is a basis for the row space. So what's the dimension of the row space? Well, we have two basis elements, right? So 2. So what's the rank of my matrix? 2. The rank is both the dimension of the row space and the column space. Numbers are the same. So the dimension of the row space and the rank you can get by looking at how many leading entries you have in your reduced matrix. Okay, so what about a basis for the column space? Well, how many vectors am I going to have in my basis for the column space? 2. The dimension of the row space and the column space are the same. So the basis for the column space of the matrix. Now, I don't know how to have to put this in a sentence, so it's going to be difficult. But that's the columns of matrix A. So notice it's the original matrix. Not the reduced row echelon form. Corresponding to the elementary columns. So the columns that have a leading 1. Of the row reduced row echelon form matrix. So in other words, I looked at the reduced row echelon form of the matrix, and the first two columns have the leading entries, so they're the elementary columns. So I would go back to my original and use the first two columns of the original matrix as my basis. So a basis for the column space in this example is I'm abusing the equality symbol here. It's the first two columns. So you have to go back to the original matrix to grab a basis for your column space. Again, it's two-dimensional, right? All right. Now, what if we wanted to find a different basis for the row space and the column space? How can we?
Why do you have to go back to the original?
Well, so row operations, which are the things we use to row reduce, right, will preserve the row space. In other words, the span of the rows in the original matrix is still the span of the rows of the reduced matrix. So row operations preserve row space, but they do not preserve column space. So as an example, a quick one, imagine you have, this is silly, but like that, right? So what's the span of these rows? Like if you're thinking this is like X, Y, Z, and you're thinking about space, the span of those the span of those columns would be the XZ plane, right? Because we have a unit vector pointing in the positive X direction, a unit vector pointing in the positive Z direction, and the span of those just gives you the XZ plane. But now, that's your matrix. Reduce it, and what would you get? Right, I got to flip the silly. It's one row operation. So now the span of these columns is the XY plane. See, so row operations don't preserve column space, even though they preserve. Now we could have done this whole course by talking about column operations as well, the equivalence kind of analogous treatment. And then we would say that the column operations preserve column space but not row space. Oh, okay, so what if you wanted to find a different basis? Okay, do you agree that, okay, if I look at the column space, of A, if I transpose A, yeah, wouldn't the columns of A become the rows of A transpose? So the column space of A is exactly the same as the row space of A transpose. Because you're just interchanging rows and columns. So clearly. So the rows become columns and the columns become rows. So the column space just becomes the row space. And so the row space of A is the same as the column space of A transpose. Again, we're just kind of relating it. So if I wanted to find a basis for, let's say, for the row space, consisting of the original rows of the matrix A, right? I would transpose the matrix. And then, so we're going to look for a basis of the column space consisting of the original sum or all of the sum or all of rows of rows of A. What can I do? Well, we know that the, oops, my bad, row space. So I want to use the original rows. Okay, when I reduce A, I get rows that are a basis for the row space, but they're not part of B. They're not any of the original vectors. So what can I do? Well, we can take advantage of the fact that the row space of A is the same as the column space of A transpose. Right, so we transpose A, you reduce the matrix. It doesn't matter what the rest of the stuff is. Of course, you're going to get the same rank regardless if you're looking at A or A transpose. But, okay. So now I look at this reduced matrix, and I see that these are elementary columns. So to find the basis for the column space of A transpose, I go back to A transpose and use those corresponding columns. So So this is now a basis for the row space of A, consisting of the original, the sum of the original rows of A. And we can do a similar, we can find another basis for the column space of A by transposing it and finding a basis for the row space of A transpose. Okay. I failed to mention something. Oh yeah. Let's phrase. How can we rephrase this question? This is just really a nose. Is the vector 1, -9, -3 a linear combination of the vectors in the set? In terms of column space, row space, null space, and all that, how do we rephrase that question? Well, to say that this vector is a combination of these is the same as saying that this vector is in the column space of the matrix, where you stick these vectors into the matrix. Phrase the question, we would say, is this vector in the column space of this matrix? Right? Because if it is, that means that this vector is a linear combination of the columns, therefore this vector is a linear combination of these vectors. No. Oh, no, I'm not. I created the matrix because I'm saying that these two questions are equivalent. just conceptually, to ask whether this vector is a linear combination of these is equivalent to asking whether this vector is in the column space of this matrix, right? Because the column space is the set of all linear combinations of the columns. So if the answer to this question is yes, that this can be written as a combination of columns, then yeah, this is a linear combination of these vectors. All right. What else? Did I forget? Oh yeah, I forgot the null space. Yeah. What is? Okay. How do you find the null space?
Les, were you going to solve that?
No.
Oh, okay.
I mean, I can. The answer is yes, and I can give you the linear combination if you want to practice. This is equal to 2 times the first vector. But you know how, of course, you know how to solve this kind of stuff. You just augment the matrix from this. Okay.
That's right, you augment the matrix with row reduction.
All right. Well, I guess I forgot to talk about the null space of this matrix, right? So we talked about row space, column space, but what about null space? Well, to find the null space of the matrix, you reduce, right? It's still the primary kind of operation. We talk about these things, reduction. So let's talk about the null space of this matrix. So we know it's the solutions, all solutions to this equation. And we would create, we would find the solution, say, by augmenting the matrix, say, with a 0 vector and row reducing. And we would get this, right? Yeah, those zeros are superfluous. And so then we can read off the solutions. Okay, how many parameters do I have for my null space? 3. We would let, say, this is like x1, x2, x3, x4, x5. This is the right hand side. So we would let x3, x4, x5 be some real numbers, say r, s, and t. So R, S, and T are any numbers. And then we can use this to solve for x1 and x2 in terms of the parameters. So x1 would be equal to negative R, negative 2s, negative t. Right? I'm thinking of this as an equation where I have to, this is 1 times R, 2 times s, 1 times t, and I got to bring this to the other side of the equation. And so x2 then is negative r, negative s, negative 2t. My null space consists of such vectors, and we see that that can be expressed as a combination of the following. Right? You just write the r's, and then you have the s's. Then 1, 0, 1, 0. And then so the null space is all combinations of these 3 vectors, so those 3 vectors span the null space. And because we got these vectors from the reduced matrix, these vectors are going to be linearly independent. So the basis for the null space is exactly, a basis for the null space is exactly these 3 vectors. So that would be a basis for the null space. So So sometimes people talk about 4 fundamental subspaces of a matrix. So can you list 3 of them? So given a matrix A, right, what are at least 3 of the spaces that we were talking about? Row space, column space, null space. Well, what would a 4th fundamental subspace be? So think in terms of matrix A, right? It has a column space, row space, null space. And what about A transpose, right? Column space of A transpose is just the same as the row space of A. The row space of A transpose is the same as the column space of A. So what do we still have to talk about? Well, the null space of A transpose. Right? That would be the 4th fundamental. Right? So we have column space of A, row space of A, null space of A, and the null space of A transpose. Sometimes you don't hear that language of 4 fundamental subspaces of a matrix. In general, are all different, but they are related. Okay, and these are not equal by any means. Okay. How would we? I'll write it again. How can we define? How would we phrase what the null space of A transpose is? Well, it's all solutions to the equation A transpose X equals 0, right? So how would you find the null space, or how would you find a basis for the null space of A transpose? Well, you transpose the sucker and you row reduce. You look at the reduced matrix. And from this reduced matrix, we can read off a basis for, or we can see what the null space of A transpose is. So we would have the last 2 variables, parameters. Those are free variables, R and S. And then these guys would have to be the 7th of R minus the 13th of S, 13th, 14th of S. So we see that it's a 2-dimensional null space of A transpose. Here's basis. So these 2 vectors would constitute the basis for the null space of A transpose. So then we want to talk about the relationship between all these fundamental subspaces of a matrix. Okay. So we already know that this relationship, these are the same. But let's think about the relationship between the column space of the matrix and the null space of the matrix. So imagine, I'm sorry, row space, my bad. Okay, row space of the matrix and the null space of the matrix. Okay, so suppose you have like your rows, matrix A, and then you have something in the null space, right? Okay, so this is, let's say, in the null space. Okay, so when I multiply A with something in the null space of A, what will I get? Zero. You get 0. Okay. So when I do this multiplication, we sometimes interpret this as taking a dot product of row with column, right? So the dot product of the first row and this vector in the null space must be 0. So what does that say about the relationship between the row and the vector in the null space? Orthogonal, right? The dot product of two vectors is 0. That's equivalent to saying that the vectors are orthogonal.
So when I say dot product, you're saying the product of two matrices.
No, so the dot product is something between vectors. Right? So, okay. 1, 2, 3. I guess 4. 2, 2.
2, 0.
Whatever. Right, so when you multiply a row and a column, you're multiplying the corresponding entries, right, and adding. That's exactly how dot product is defined for Euclidean vectors. Right, so, okay. And of course, then you take the second row of your matrix, then you dot it with this column from the null space of A, and you get 0. So this thing in the null space is also orthogonal to the second row. And the same thing with the third row. It looks like that if you take a vector in the null space, it has to be orthogonal to all the rows of the matrix, right? So every vector in the null space of A is orthogonal to all the rows of matrix A. So this says that we can now talk about characterize this as saying that the null space is orthogonal to the column space. Everything in the null space of the matrix is perpendicular to the row space. The null space of the matrix A is orthogonal to the column space. So, of course, if I look at the same matrix again, but I think of it as consisting of columns instead of rows. This is tricky, okay. And suppose that this is a vector that I wrote as a row, and this vector comes from the null space of A transpose. So you essentially have something like this. X is in the null space of A transpose. So that means that A transpose times X is 0. Transpose both sides. And you get this. So that's X transpose times A equals the 0 vector transpose. So what does this say about the relationship between this vector in the null space of A transpose and the columns of the matrix A? They're orthogonal, same reason, right? Row dot column to give you 0, so this is orthogonal to the first column of A. Likewise, this is orthogonal to the second column of A, and so forth. So this says that null space of A transpose is orthogonal to the columns. Oh man, jeez. Okay, stop me. If everything in the null space of A is orthogonal to the rows of A, so the null space of A must be orthogonal to the row space. Likewise, the null space of A transpose is orthogonal to the column space of the matrix. Sorry about that. Okay. And this brings us to, well, a picture, I guess, and then the rank knowledge theorem, and then we can do some stuff that's maybe relevant to you. Okay, so if you had an n by n matrix, your column space would be in what? Would be your columns live in what space? So the columns of A consider as vectors in Rn, right? The rows of A consider it as vectors in Rn. So we have n entries. And now, so if you have Rn, okay, the null space is going to be a subset of what? The null space, matrix A, right? So if you take something from the null space to get the zero vector here, how many entries would we have? Well, n of them, right? That's a n by n matrix. This has to be n by 1 for the multiplication to be defined. So the null space of A is a subset of Rn. Now, the row space as well is a subspace of Rn, right? So the row space matrix is a subset of Rn. And we said that the null space of A is orthogonal to the null space of A is orthogonal to the row space, so I'm drawing it this way to indicate orthogonality. Okay, now look at the Rn. The null space of A transpose is a subset of what dimensional space? So if you transpose this, you get a n by n matrix. So if you have something in the null space of A transpose, this has to be an n by 1 column. So the null space of A transpose is a subspace of Rn. And what do you think this would represent? Column space of A. And we said that the null space of A transpose is orthogonal to the column space of A. So that's a picture. Help you remember some of the relationships. So now let's look at the rank nullity theorem. It says the following. The rank of the matrix plus the nullity of the matrix. So the dimension of the row space or column space of the matrix plus the dimension of the null space of the matrix has to equal to, so I'm going to say A is n by n, right? Is n. Or if you'd like, it's the number of columns in your matrix. So the rank plus the nullity equals the number of columns you have in your matrix. And of course, we can apply this to A transpose as well. So the rank of A transpose plus the nullity of A transpose. Okay, spelling. Would be equal to what? N, right? If you transpose A, you have an n by n matrix. So that would be the number of columns in A transpose. Or, so how do I interpret this using this picture? Well, okay. So suppose that, so here the dimension of the row space of A is the rank, right? Let's call that R. That's rank. And the dimension of the null space is called nullity. And as it turns out, these are orthogonal complements in Rn, so the sum of the two dimensions has to add to n. So the dimension of the null space will be n minus r. Right? That's what rank nullity theorem says. The rank of the matrix R, the rank of the matrix A, let's call that R, plus the nullity of the matrix has to equal to the number of columns, so that's n. So this must be n minus r. So in our example, when we had this 4 by 5 matrix, we saw that the row space of A had a dimension which was, let's look at the row reduced matrix here. We had this. Right, so we see that the dimension of the row space was 2. We had 2 leading ones, 2 non-zero rows. So that was 2. And what must the dimension of the null space be then? It must be 3, right? By rank nullity theorem. So rank of A plus nullity of A is the number of columns. It's 5. Rank is 2 because rank is the dimension of the row space and the column space. 2. So this must be 3. And so in our example, we can see that the null space was the span of 3 vectors. I forget what it was, but it was the span of 3 vectors. Right? I don't know. I didn't write that information. So 3-dimensional, or 3 independent vectors. So that was the basis. So now you can maybe, using this, talk about the maximum rank of the matrix, the possible maximum rank. So suppose you have a 3 by 5 matrix. So A is 3 by 5. What's the maximum possible rank of this matrix? 3. Yeah, you can't have more linearly independent rows than you have rows. So the maximum rank is 3. The max possible, we don't know what it is. Okay. So what can we say about the null space? So if we have rank nullity added together has to give you 5, right? Number of columns. So if this is at most 3, what is the nullity of A? What is nullity of A at least? At least 2. So you have at least a 2-dimensional. So the rank, sorry, the nullity of A then must be at least 2. Could be more. Right? So you have to play that game. Right? So let's maybe turn that around. Suppose we have a 5 by 3 matrix. What's the greatest possible value for the rank of A? 3, right? Because you can't have more linearly independent columns than you have columns. So what about the nullity then? Must be equal to 3. So if this is at most 3, then this would be 0, right? If the rank of A is 2, then this would be 1. If the rank of A is 1, then this would be 2. Where the rank were 0, so i.e. suppose they gave you a matrix, a 0 matrix, so that's kind of silly, but if the rank were 0, then this would have to be 3. So the nullity, well, I guess you can say it's at least 0, right? And at most 3. Here the nullity is at most 5. All right. Okay then. What's that?
So the rank is like the basis, essentially? Or
The rank
similar?
is the number of basis elements for either the column space or the
Right,
row
the
space.
dimension. And then the nullity is like, kind of like the extra columns, so like linear combinations of the basis, in a way.
The
That's
nullity
kind of like
is a number, and it's the dimension of the null space. Right? So the null space is the subspace.
Right.
The nullity of the null space. The nullity is the dimension of that null space. So it's the number of basis elements in your null space. The number of basis elements for a basis for the null space. So yeah, if somebody says the nullity of the matrix is 3, you know that your null space will have to, the basis for your null space has to consist of 3 vectors, for example. All right, let's do an example that's a little, well, hey, number 1 in your homework, what can I say about that? Okay, so, no, not the answer.
That's what you can say about it.
Okay, so, okay, A is invertible, right? So what can I say about the null spaces there? If A is invertible, yeah. Well, it consists of the 0 vector. It's the dimension of the nullity of 0. But how do we know? So if A is invertible, so we know that we can reduce it, well, to the identity, I guess. And so if you reduce the matrix and it's the identity, it's an n by n matrix. How many leading ones do you have? N, right? So the rank is n. So the rank of the matrix A would be n. The nullity must be 0, because of course that has to equal to the number of columns. So now suppose you have another matrix B and it's n by n, but you're not told whether it's invertible or not. So that's the setup for your problem 1. And so I'll flip this around and I'll ask, what can we say about B times A? What can we say about the row space of B times A, right? Can you tell me what the row space is? What can you say about the row space of A? Well, so what can we say about the column space? Well, they're both Rn, right? Because we have, because it's this matrix is invertible, we see that the column and row space are both n-dimensional. Rank is n. So the rows must span all of our n-dimensional space. The columns must span all of our n. So, all right, what can we say about the row space? Well, what can we say about, say, the null space? B times A times x is 0. What are the solutions to this?
All of x is 0. All of x is 0.
X has to be 0?
No,
actually,
because
I
B
don't.
can be,
I can't say anything about X to B because
B can be the zero matrix.
right, exactly. Right. So I can't say anything. Right. So on your homework, so they did it the other way around. So they had A times B, and they want you to prove that the row space AB is the same as the row space of B. And the only thing I can really tell you is to think about the fact that since A is invertible, you can reduce it to the identity, and you do that via a sequence of elementary row operations. And B, you apply a sequence of row operations. I don't know what they would be. And you will get RDF. And now think about multiplying A and B and applying the sequence of row operations. It's just talk what's going to happen. Okay, that's my hint. All right. So the other interesting problem in your homework is the one with the polynomials. You have some time, awesome.
Where is that one?
I don't know.
I think it looks kind of good.
What number is it?
Check out
So that was pretty. I thought it was a pretty challenging problem in the sense of like, what do I do? How do I relate these matrices and null space and all that? So here's a set of vectors from P3. So these are 4 elements in P3. 3, right? So these are polynomials of degree 3 or less. Subset of P3. Polynomials of degree 3 or less.
You lower some of those numbers by just dividing through, like by
Yeah, probably. And
just maybe a little bit.
yeah,
Okay.
definitely we could. For some reason I didn't. So
Okay. Just didn't know if you could or not. Or,
So, okay, what if we wanted to find a basis for the span of those polynomials, for those vectors, right? So find a basis. It's called a set S. So it's a span of S. So you imagine all possible linear combinations of these 4 polynomials. We'll get a subspace of P3, and we'd like to find a basis for that subspace. So what can I do? Well, if you look at the standard basis for the P3, it would be like this. You have 1, x, x squared, x cubed. That would be a basis for P3, standard basis. Right? Any polynomial with degree 3 or less can be expressed as a linear combination of these independent functions. And so let's turn these guys into coordinate vectors with respect to the standard basis. So the first polynomial would become 1, negative 2, 0, 0, right? Because 0 times x squared equals 0 times x cubed. The next guy would become 2, negative 5, negative 3, negative 2. Yeah, that's the coordinate vector with respect to our standard basis of this guy. Oops. That would be 0, 5, 15, 10. The third polynomial, and then 2, 6, 18, 8. So these are the corresponding coordinate vectors representing each of those polynomials relative to the standard basis. So now we can rephrase the question and say, can we find a basis for the span of these 4 column vectors? So I'm rephrasing the question in terms of matrix algebra and all that by using coordinate vectors. So can we find a basis for the... Right, so that would be the same as saying, find a basis for the column space of the matrix or the row space of some other matrix. So if I just want to find a basis, I would perhaps stick these vectors into rows. To create a matrix. Call this matrix A. So if I wanted to find a basis for the span of these vectors, I would find that they'll be the equivalent as finding a basis for the row space of A. Yes?
I've always been confused. Like how do you come up with that matrix, like all the values in it?
Well, okay. I know that I can find the basis for the row space of this matrix, right? By row reducing. And the basis for the row space will consist of the non-zero rows of RREFA. So I can take advantage of the fact by taking these columns, these vectors, and sticking them into rows of that matrix. So if I find a basis for the row space of this matrix, that's the same thing as finding a basis for the span of these vectors.
I mean, like, I guess I'm seeing 0, -2, 10, 8, like that's on the bottom. And then you have it, set right there, and then on the matrix, I'm guessing you kind of...
Did I mess something up? Or,
Oh, no, I'm just like wondering like how you get all the values for A in A.
So this vector, I wrote as a row.
Okay.
This vector, the second one here is 2, -5, -3, -2. So I stuck them in the second row itself. So then we row reduce. and I get okay. So we have these rows are non-zero, so those rows are basis for the row space of the matrix. So the basis for the row space of the matrix, or equivalently the span of those vectors.
Are you sure about that reduction?
What?
What you got into a calculator? It's something else. Let's see.
Okay.
Do you need all the negatives?
Yeah. 1, -2, 0, 0. 2, 4 by 4, each 2.
Oh, yeah. So we missed something out. I might just go on even if it's wrong, so. Last one, 2. Might just have to go on even if it's wrong, if that makes sense.
Because actually, leading ones there would be now be 3 instead of just the 2.
Oh, okay. Yeah, I know what you did. Okay, I just wrote down the wrong matrix, so it's fine. We're good. Let me write down the correct thing. Okay. Yeah, I know what I did. This is the row reduced echelon form of A transpose. I just wrote down the wrong thing. My bad.
So really quickly, only the rows can be a basis, it's not the columns.
No, we're going to use columns. Well, basis for what, I guess, is the question. The columns, you can get a basis for columns.
So that A matrix is transposed already?
No. I'll write down the reduced echelon form of the matrix right now.
Oh, okay.
Sorry, I was just looking at the wrong matrix in this piece of paper.
Okay, cool. Yeah, but I think it's transposed in.
Okay, now we have all the information on the board. Let's finish this up. Okay, so a basis for the row space of matrix A would be the non-zero rows right? But remember that these non-zero rows are coordinate vectors for polynomials in P3 relative to the standard basis. So, what polynomial does, let me write it here, what polynomial does this coordinate vector represent? 1 times 1 plus 0 times x plus 0 times x squared minus 2 times x cubed. So that represents the polynomial 1 minus 2 times x cubed. This coordinate vector represents the polynomial x minus x cubed. And this polynomial represents x squared plus x cubed. I mean, that coordinate vector represents this polynomial. So this is the basis for the span of S. Okay. But on the homework, they asked you to find, okay, so the wording was, find a subset of S, which is the basis for the span of S. So the way to interpret that is to say that they're looking for a basis for the span of these 4 polynomials consisting of some or all of these polynomials. So we have to take some of these polynomials and say that they are a basis for the span of all of these polynomials. So how many of these polynomials are we going to have in our basis? 3. Right, we already know that it's 3-dimensional. The span of those 4 polynomials is 3-dimensional because we found a basis that consists of 3 elements. So we're going to take 3 of these polynomials. Now, which of the 3 polynomials will make a basis? So we're going to find basis for the span of S consisting of elements of that. So some or all polynomials. So the way we did it here at the basis did not consist of the original polynomials. Right? They were different. So what can we do? Well, what we're going to do instead is take our coordinate vectors, which I erased, unfortunately, and we're going to stick them into columns of the matrix. Let's call that matrix D. So you're going to have 1, -2, 0, 0, 2, -5, -3, -2. Again, just coordinates. 0, 5, 15. So of course that's just the transpose of my A. Right. And now we're going to row reduce.
So can we label it like A transpose instead of B?
You can't.
Okay.
And then we're going to find the reduced row echelon form of the matrix. All right. And now, right, so the idea is that if we want the basis for the column space of this matrix, right, consisting of some or all of the original columns, we can row reduce and use the columns in the original matrix corresponding to the elementary columns in the reduced matrix. That's how we found the basis for column space, right? So I see that in the reduced matrix, columns 1, 2, and 4 are elementary columns. So a basis for the column space of my matrix is first, second, and fourth column of the original matrix. So just that standard procedure of finding a basis for column space. By row reducing, we're using the original columns corresponding to the elementary columns in the reduced matrix. So if this is the basis of the column space of our matrix, then what would be basis for the span of S consisting of the elements of S? The basis for the span of S consisting of the elements of S. Well, we would have, let's see, the first, right? The first polynomial, and then, of course, the second one. And the fourth one. That would be one answer to the question. Here's the basis, the span of S, using 3 of those 4 polynomials. Oh, go ahead.
No, I mean, before that, you found a basis also.
Right. Well, the difference was that I found a basis, so any old basis for the span of S, but it didn't consist of the original vectors. Here, really specifically, you're asking for a basis for the span consisting of the elements of S. Now, one thing I did forget to mention, though, we could easily, right? So one of these vectors is linearly dependent on the other 3, and so how can we write this vector, which we left out of the basis? We know that it's in the span of these 3 because these 3 made a basis, right? So this must be a linear combination of basis elements. And what is that linear combination? Well, you can easily find what that linear combination is by looking at this reduced matrix. Okay, so this says that, so if I just have vectors, v1, v2, v3, v4, this tells me that v1 is the negative. Okay. Now, what does this tell me? This tells me that V3 can be written as 10 times V1 minus 5 times V2. So you can use this matrix to find the linear combination of this vector in terms of the other ones. And there we go. We can easily show that that's true. And it indeed is 0. Yes, is that true? Maybe, maybe not. That's all I have. The last part was starting with this, extend this basis so that you have extend this to a basis for V3. Okay. So the way you do that is by actually finding the null space of V transpose. But if you want to know why or help, come by the math.